Thanks, Laz. Well, I don't think I need to start off by convincing you that lithospheric boundaries are important. We've had two great talks by Kate and Sandra emphasising that. But what I want to talk more specifically about is where those lithospheric boundaries are within the Gawler Craton. So the traditional way we've had about thinking about boundaries in the Gawler Craton has largely been drawn from the magnetics. So this map shows the domains of the Gawler Craton, which are defining regions of mag low and mag high mainly. And on the other side we've got the time-space plot, which defines the detailed stratigraphy that occurs in these areas. The magnetics, the signal is really dominated by the response of the upper crust. So in the Gawler Craton, a lot of these boundaries are defined by the distribution of intrusive rocks, which are often very magnetic, or the metamorphic grade of the cover sequences. But you can see in the time-space plot that a lot of these domains actually share a common geology. So my question is, how significant are these boundaries? Are these distinctions that just exist within the upper crust, or are these boundaries that also reflect differences in the mid-crust and lower crust? So lithospheric boundaries are big structures. They extend from the upper crust often into the mantle, separating different basement elements. And we're often not going to see them at the surface. They might be covered by younger sequences. And these boundaries could have originated as like paleosutures during accretionary or collisional events. They could be strike-slip faults or basin or orogenic faults which become reworked. So we know they're important because big structures are prone to tectonic reworking and fluid flow. They're convenient or easy places for mantle magmas to ascend, and they can often connect to enriched zones in the mantle. So this map shows an example of a copper gold mineral system in Papua New Guinea, which are all associated with a paleosuture shown in the heavy black dark line, which marks a belt of ophiolites. So the suture formed during accretion, and then later on magmas ascended along this structure, and mineral systems formed. So what's the surface footprint of lithospheric boundaries? Well, they're not going to be discrete structures where we can have one foot in one element, the other foot on the other. They're going to be broad zones, which means that they might be difficult to detect at the surface. Okay. And these are some of the tools we're going to use to do it. So obviously mapping and drilling and magnetics giving us lots of information about the upper surface, but there's other techniques that we can use to probe a bit deeper into the crust. So we've already heard a lot about MT today, and how that can map fluid pathways, which are often associated with big lithospheric structures. There's also other deeper probing data sets that we can integrate with the MT. So gravity is one of those, seismic tomography models, reflection seismics, and also isotopic chemistry. So what we're going to do now is take a look at some of these different data sets and for the Gawler Craton, and see where we can find big gradients which might relate to structures. So we'll start out by looking at the gravity. So this is the state gravity that's been upward continued to about the equivalent of 30 kilometre depth, and we can see that there's some big gradients in the data. So the southern part of South Australia has been affected by the opening of the Great Southern Ocean, which it's created a gravity high along the southern coast, but we can see we've got a high region on Northern Eyre Peninsula, we've got a broad low region in the central part of the craton, and then in the north. And the gravity compares quite well with seismic tomography data. So the second plot comes from OSRAM, which is it's a model of the P wave and S wave wave speeds. And these wave speeds are dependent on temperature and on composition. So the ratio of P and S waves can be a bit of a proxy for composition. So low ratios are more felsic rocks, and higher ratios are more intermediate or mafic rocks. So we can see in this data set that the high PS wave ratio corresponds to where we've got the gravity high, and also the lows correspond. So these big gradients are potentially significant structures within the mid and lower crust. We can also compare these data sets with seismic reflection. So I'm going to go through 3 of the big seismic reflection surveys in the Gawler, just to look at how the locations where we've got gradients in the gravity and seismic tomography match the interpretation of the reflection profiles. And you can see here in the Goma line, which goes from the central part of the Gawler to the north, shows some offsets in the Moho which correspond with the gravity gradients and with one of the gradients in the seismic tomography data. So it's 2 data sets pointing to there'd be a boundary in the same place. And this is the Euclid line. So we've also got a correspondence with 2 of the gradients with places where the Moho's been offset. And then finally the Eyre Peninsula line. So it shows an offset in the Moho which corresponds to the eastern side of that VPVS high. I'm going to move on to some isotopic geochemistry now. So this is a way that we can get an indicator of what the age of the mid and lower crust is. So felsic igneous rocks are derived from a combination of fractionation of mantle magmas and crustal melting. And we can use whole rock neodymium model ages and hafnium in zircon model ages and inherited zircons as a proxy for what the lower crustal reservoir or source region for these granites is. So this data set I've got point data for those 3 different data sources, as well as a grid. There's about just over 300 data points in there. Works particularly well for the southern part of the Gawler Craton, where we've got the most data. I think you can see that we've got a broad region on the west coast where the rocks have Paleoproterozoic ages. We've got a Mesoarchean belt through the Eyre Peninsula, and then on the eastern coast of Eyre Peninsula and York Peninsula, perhaps continuing up to the north, we've got Neoarchean belt. In the northern Gawler Craton, we've got much less data, but the isotopes suggest that there is Mesoarchean and Neoarchean basement underneath the cover sequences of places like the Nawa domain, and some quite a small number of more juvenile or younger Paleopro ages. So this is another data set we can use to try and identify where we've got big boundaries between particular regions. Okay. And then finally, looking at the MT. So Kate's explained to you that we've got big conductors along the eastern Gawler Craton, under York Peninsula and Eyre Peninsula, and then there's a more arcuate trend just north of the central Gawler Craton. Right, so now I'm going to try and integrate these data sets to come up with best model for where I think the major lithospheric boundaries in the Gawler Craton are. And they don't account for every little variation we've seen in these data sets, but I've tried to pick boundaries where the different data sets agree with each other. And so I've divided the Gawler Craton into 5 different elements. So the first is where we have Mesoarchean basement, largely drawn from the isotopic data. And the high gravity and high VPVS ratio coincides with where we know that these Mesoarchean rocks crop out. Then I think we have a distinct belt within the eastern Gawler Craton. So the boundary between these two elements coincides with where the Kalanjala shear zone is. So the Kalanjala would just be a discrete shear zone that's reworking this broader boundary. So we see a gradient in the VPVS data. There's an offset in the MOHO, in the crustal reflection survey, and this boundary is flanked by those 2 big MT conductors. And then in the north, so we saw in the MT that arcuate conductor north of the central Gawler Craton. Well, that coincides where the Karari shear zone is. So I think that shear zone's reworking another big boundary. We saw an offset in the seismic along this boundary, and there's a sharp gradient in the gravity for part of this boundary. This corner of the Gawler Craton is going to be the focus of Tom's talk, but this boundary coincided with that big gradient in the gravity and the VPVS ratio. And then finally, we've got the northwest part of the Gawler Craton, and this boundary is largely drawn from the isotopic data. So we had that sharp contrast between Paleoproterozoic model ages and Archean model ages. And there's also an MT conductor along its northeast boundary. So the Karabi, Albrinda and Olabinda shear zones would all be surface expressions of where this big boundary sits in the lower crust. Okay, and just to link back to the original idea that these boundaries connect with mineral systems, we can see that Hildeberg granites, well, their distribution has been governed by where these boundaries sit. So the big boundaries are easy places for magma to intrude and to ascend. So they're shown in red. There's also a correlation between mineral occurrences. I've shown gold and copper here. And our 2 big metallogenic provinces in the Gawler Craton, the ISCG province and the Central Gawler Gold province, both sit on 2 boundaries. I guess I'm not necessarily telling you anything you don't know, but sort of a proof of the concept that we do find mineral systems associated with these boundaries that we derive from other data sets. So carrying on with the concept of using big boundaries for exploration, I think you can, so in the other map we can see the distribution of exploration drill holes that intercept basement. There's broad areas within these predicted boundaries which might be places where these known provinces can be extended or new places for exploration. Okay. Thanks very much for listening.